I will let you do the takeoff today. Are you ready for that?
Since I know how to taxi and I know how to climb, the takeoff is just a way to transition between those two things.
Smoothly increase power. Airspeed is alive. The airplane is accelerating properly. Use your feet to stay on the center line. Now start to pull back into climb attitude. Great first takeoff.
Within your first few flight lessons, your instructor will begin teaching you how to do a standard takeoff. Once you've gained proficiency with that, your instructor will start teaching you how to modify that technique to account for some special circumstances like crosswinds or gusty winds. This lesson will cover only tricycle landing gear. For those that are interested in flying airplanes with tailwheel landing gear, that will be covered in a separate lesson. We'll start by talking about a standard takeoff. Then we'll talk about how you modify that technique to correct for crosswinds. Then we'll talk about how you correct for gusty winds. And finally, we'll talk about how to handle an aborted takeoff. Specialty takeoffs like short field and soft field takeoffs will be covered in a different lesson. A takeoff can be broken down into three phases: the takeoff roll, rotation, and the initial climb. During the takeoff roll, the airplane is controlled using the methods from the lesson controlling an airplane on the ground, with one exception. In that lesson, I said that you need to keep the speed low. During the takeoff roll, your objective will be to build up speed. During the initial climb, the airplane is controlled using the methods from the lesson Airplane Primary Controls. To start the takeoff roll, you'll increase the power gradually to full power over the course of a few seconds. That provides time for you to recognize and correct for any secondary effects that happen because of the change in power setting. Typically, some right rudder is needed. As the airplane accelerates, the aerodynamic controls will gradually become effective, but the elevator and the ailerons are still not primary controls. The 3-point attitude is your best attitude during the takeoff roll because it minimizes drag, and as we'll discuss when we talk about gusty winds, it has other advantages. You use the rudder pedals to stay on the center line. Even with full castering nose wheel, the rudder will be effective enough to use for steering during the takeoff roll. There's no need to be using differential braking. The airspeed indicator will sort of wake up when you get around 20 to 30 knots. It'll go suddenly from 0 knots up to the actual airspeed. When you get around that speed, you need to glance down at the airspeed indicator to make sure that it is actually working. Rotation is how we transition from ground-based control to in-flight controls. It's called rotation because the airplane rotates about the axis of the main landing gear during the maneuver. You'll start the rotation as you approach your initial climb speed. Usually, your initial climb speed will be the best rate of climb airspeed, which is called V sub y. Since the airplane will continue accelerating during the rotation, you'll start the rotation about 10 knots before you get to that speed. You use the airspeed indicator to help you decide when to start the rotation. As you get more comfortable with the airplane, you'll also develop a sense for what the elevators and ailerons kind of feel like as you get to that speed. Your ground speed won't always be the same. It will vary depending on wind conditions and depending on the density altitude. The published VY speed for your airplane is at gross weight and sea level. When we get to some later lessons, we'll discuss how VY can change based on how heavily you've loaded the airplane and based on your altitude. You use the elevator to gradually raise the nose wheel off the ground. You want to establish a pitch attitude that corresponds to what you will need in the initial climb. And you'll know how to judge that based on experience after you've done it a few times. This pitch change may have some secondary effects that you need to compensate for. Typically, it will require some additional right rudder. Once the main wheels lift off the ground, then your rotation phase is complete and you'll start using the rules for controlling an airplane in a climb.
On this next takeoff, you will need to correct for a crosswind.
I thought you said we weren't going to learn specialty takeoffs until later.
You will have some degree of crosswind on a majority of your takeoffs, so handling that is part of a standard takeoff.
Before we talk about how to compensate for a crosswind, let's talk about what would happen if we didn't compensate for the crosswind. This shows an airplane at the beginning of a takeoff roll viewed from behind. Notice that the wings are not level. The wing tips are somewhat higher than the wing roots. This is called dihedral, and it will affect how the airplane behaves in a crosswind. These red arrows illustrate the forces on the airplane without any wind. The weight acts through the center of gravity, and that is reacted by forces at each of the three wheels. Now let's consider what happens when we have a little bit of wind. The wind pushes on the side of the airplane, and it also pushes on the tail of the airplane. The wind force on the tail tries to turn the airplane to the left. The wheels are able to react these forces because there's still plenty of force on the wheels holding them down, so they can generate a friction force to react that side force. As speed builds during the takeoff roll, due to this dihedral, the left wing will start to develop positive lift and the right wing will start to develop negative lift. Weight gets shifted from the left wheel to the right wheel to compensate for this. If the weight on the left wheel ever goes to zero, then the airplane will begin to bank to the right. When you begin your rotation, you'll lift the nose wheel up off the ground and the wings will begin to generate net lift. The left wing generates more lift than the right wing due to the dihedral effect. There's a lot less weight supported by the tires, so their ability to resist side forces goes down. Before the airplane lifts off the runway, it begins to slide to the right, yawing to the left due to the force on the tail, and banking to the right due to the extra lift on the left wing. Maybe you'll be able to lift off before you reach the edge of the runway. Maybe once the airplane's in the air, you'll be able to level the wings and get the aircraft under control before you hit something. On the other hand, maybe the right wheel will suddenly regain traction and you'll swerve to the left due to the left yaw. A competent pilot does not leave the outcome up to maybes. Now let's talk about a takeoff roll with proper compensation for the crosswind. Here we see the same airplane from the rear with the same forces that it has at the beginning of the takeoff roll. But this time, the pilot is going to move the yoke to apply full left aileron. As speed builds during the takeoff roll, the pilot gradually reduces the aileron deflection such that the ailerons will counter the dihedral effect plus a little bit. So weight is shifted from the right wheel to the left wheel, but not by enough to cause the airplane to bank to the left. Also, you'll apply some right rudder pressure to reduce some of that weather vaning tendency. Now, when you begin your rotation, you'll lift the nose wheel off the ground and the wings will begin to generate net lift. The right wing generates more than the left due to the aileron deflection, but weight remains on the left wheel until just before the airplane lifts off. As the airplane lifts off the runway, it begins to bank to the left and to yaw to the left. Once the airplane has turned enough to establish a crab angle, then you'll level the wings and you fly away, tracking the runway centerline.
So, do I need to do that on every takeoff? Even if there is only a little bit of crosswind?
The amount of aileron deflection that you need to maintain changes based on the strength of the crosswind. When the crosswind component is small, the effects of not compensating are also small. But you should do it anyway. Now, let's talk about gusty winds.
A wind gust is a sudden, temporary change in the wind speed. Gusts are caused by vertical columns of air that strike the ground and spread out. As they spread out, the velocity drops off. The vertical column and the gusts along the ground move around with the steady wind. If an airplane flies directly through the center of that vertical column, then it will experience an increasing headwind as it approaches the column, a rapid switch to a tailwind as it passes through the column, and then a gradually decrease in the tailwind as it flies away. If the airplane passes a little off to the side, then it will experience a strong crosswind as it goes past that center. The airplane is most vulnerable to these gusts during the rotation phase of the takeoff. Let's first consider the effect of a crosswind gust. If you get a sudden increase in the crosswind component, that has the same effect on the airplane as if you had not corrected adequately for the crosswind. So if you had a 5-knot steady crosswind and you did everything right in order to correct for that crosswind, but just as you start to rotate, the crosswind suddenly becomes 15 knots, then the effect on the airplane will be like a 10-knot crosswind that you didn't correct for. Similarly, if the crosswind gust component decreases rapidly, then you'll end up with too much correction. So if you were correcting for a 15-knot crosswind and suddenly it drops off to 5, then you will have put in too much aileron and you'll bank into the wind as you rotate. Now let's consider the effect of a headwind that suddenly decreases because of a gust. Here we have an airplane rolling along the runway. Let's assume it just now reaches its rotation speed. As it rotates, it starts to climb. Suddenly, the headwind component decreases dramatically. The wing lift decreases, so the airplane either comes back down on the runway or it may wallow along for a little while and fail to gain altitude for a while. So is it a big problem that the airplane came back to the runway? Well, that depends. If the airplane started to drift sideways or to yaw while it was airborne, then when it comes back down and hits the runway, there will be side force on the wheels. Remember that it's not uncommon for there to be a crosswind gust happening around the same time as this headwind change. Is it a big problem if the airplane wallows a while before it starts climbing? Well, not if the pilot's patient and waits for the airspeed to build up, but if the pilot panics about the failure to climb and pulls back, then the airplane may stall. If the pilot panics about the airspeed being too low and lowers the nose, then the airplane may hit the ground on the nose wheel. An alternate technique for takeoff is to put the airplane into a climb attitude early in the takeoff roll, and then instead of affirmatively rotating as you get to the right speed, the airplane will just fly off on its own whenever it reaches the right speed. That works pretty well in steady winds, but let's consider what would happen if you use that technique in gusty winds. Here, as the airplane is accelerating on the runway, a wind gust suddenly increases and the airspeed is enough that the airplane lifts up. A pilot that's surprised by that will tend to push forward on the stick. Since gusts are temporary, this headwind component may go away as fast as it came, may even turn into a tailwind component. The airplane sinks back to the runway.
Gee, I don't want any of those things to happen to me. What do I need to do to make sure they don't happen?
In gusty winds, it is especially important to keep the nose wheel on the ground until rotation. Increase your rotation speed by at least half of the gust factor. Then rotate assertively. You can reduce your speed to normal climb-out speed when well clear of the ground.
Wouldn't that use more runway?
Unless you have a very short runway or you have obstacles to clear, that trade-off is worth it.
During the takeoff roll, you checked whether the airspeed indicator was working and whether acceleration was normal. What would you do if it wasn't?
Let's talk about aborted takeoffs.
Aborting a takeoff before rotation speed is really no big deal, so you should never hesitate to do it if anything isn't right. If you're aborting the takeoff before rotation, you'll just reduce the power to idle, then you'll use the brakes to whatever extent you need to so that you can stop on the remaining runway. After rotation, it gets a little more complicated. You'll reduce the power, then you need to lower the nose, and then you need to transition to whatever phase of landing would be appropriate for your altitude. Lowering the nose to maintain your airspeed is crucial at this point. Airplanes slow down very rapidly if you reduce the power and the airplane is in the climb attitude. Once you're too far along for you to land on the remaining runway, then you shouldn't abort the takeoff unless there's a very serious problem. The correct course of action at that point is very situation dependent. We'll talk more about the different options when we talk about emergency landings later. At some point you may have gained enough altitude that it might be possible to make a 180-degree turn back to the runway. That maneuver has been called the impossible turn because a lot of people have attempted it and have stalled and spun. So unless your options for doing anything else are really bad, then turning back to the runway is probably a bad choice.
Nice job on takeoffs today. We will work on specialty takeoffs after your first solo. Once you are a little more comfortable with controlling descents and flying at slow airspeeds, we will start working on landings.